Welcome to yet another session in chemistry, and today we are going to discuss atomic structure. It's a very important unit, and for the last 3 or 4 that competitive examinations, a number of questions have been asked in this lesson. As usual, we discuss as many problems and discuss the concept then and there. Let us move on to problem number 1. Refer problem number 1. And this is based upon what's called the Palmer's equation. Palmer's equation, that is for the calculation of the wavelength or wave number in the hydrogen spectrum or single electron systems. For example, mu bar, that is the wave number, is equal to 1 by lambda, that is also equal to the Rydberg constant, and z square, this is the nuclear charge, and now we have 1 by n1 square divided minus 1 by n2 square. And this is the lower orbit, is the higher orbit, and is the Rydberg constant. The Rydberg constant has the value 1.09677 into 10 power 7 meter inverse. So for the calculation of wavelengths, it is better to have some ready-made figures. For example, the transitions 2 to 1, that is Lyman's first line, and 3 to 1 Palmer's first line, 4 to 1 Paschen first line, and 5 to the here see 2 to 1 Lyman, and 3 to, better write 3 to 2 for example all the first lines we can consider Palmer's line, and 4 to 3, just add 1, 4 to 3, that is Paschen, and 5 to 4 bracket, and 6 to 5 fund series. So if you know this portion as a ready-made figure, very easily we can solve the problem. For example, this equation we can modify. Suppose we want to calculate lambda. So lambda means, so this portion, if it is x, then what happen? This x divided by this entire thing, x into RH into z square is equal to lambda. Therefore, lambda must be equal to, for example, this portion I am taking it 1 by x. Instead of taking x as a whole, better this portion, so 1 by x. Then lambda RH and z square will go to the denominator. And this figure, if you know correctly, then if the wavelength is given, very easily we can calculate which transition the line belongs to. As far as this problem is concerned, the wavelength given is 1600, that is 1642 angstrom unit. 1642 angstrom unit. For this wavelength, what is the transition correspond to? And here, if you solve this problem by using the available data, we have the answer 7.2. That is 7.2 is like this: n1 square n2 square divided by n2 square minus n1 square. So this portion simplified, and this will give 7.2, that corresponds to the transition 3 to 2. That is, the excited electron returns from the third orbit to the second orbit, and this option is given by 2. So better select option 2, transition 3 to 2.